The problem states, determine the moment of inertia of the beam's cross-sectional area about the x-axis. So first, let's talk about how we determine moment of inertia. So if we have a rectangle that we know the dimensions of, where the base will be shown with the letter B and height is just h. About its center of mass, if we're looking at its moment of inertia about the x-axis, then we characterize the moment of inertia by 1 over 12 times base times height cubed. And this is the moment of inertia about the x-axis with the axis going through the center of mass right here. So now let's consider another case where we're talking about a rotation where it is this axis, which we will show with the x prime. So how do we calculate the area moment of inertia about this new axis? It does not go through the center of mass here. In that case, we would use this equation where the x prime, so the second moment of inertia about x prime, will be shown by the original moment of inertia calculation, where we assume it goes through the center, the center of the rectangle. So that will be shown with this I sub x, and we will add the value area times d squared to this quantity, where d is defined by the distance between that axis and the center of mass of the rectangle. And this is called the parallel axis theorem. This doesn't apply just for rectangles. It applies for any shape. So now let's take these equations and apply them to our system. So first, we will start with a diagram of what's happening. This is a 3D diagram, and we want to have a 2D because it's asking about the cross-sectional area. So we have this rectangle here, like that, and we have two more, like this. This is our cross-section. And now let's draw the horizontal axis here, where this is the x-axis. And now we're in a position to sort of see how to set up our total moment of inertia equation. I will mark each center of mass of the rectangles with the blue color as such, and I will tell you the distance between the x-axis and each center of mass with this blue distance indicator. So we see in the diagram it says 2 inches for the width of this rectangle and 4 inches for the width of this rectangle. So that means a total of 4 between these two locations. And between this blue dot and the x-axis, we have a distance of 1. So I will show it like this, where we have a distance of 1 between those two locations. And that is given to us by the height of the top rectangle here. 2 over 2 is obviously 1. At this point, we can start solving the problem. So moment of inertia equals this top rectangle here. So we'll show that with the moment of inertia I sub t for top. And we have these two bottom rectangles here. And notice the symmetry. We don't need to calculate this and then calculate it again. We can just times so we can just do this, plus 2 times I sub b, where I sub b is the second moment of inertia of the bottom rectangle here. There's 2 of them, so we utilize symmetry for that. So this is our expression. Now let's rewrite this by substituting the values we know to calculate a numerical value for I sub t and I sub b. For I sub t, we see that the x-axis, or our axis of rotation, does not go through the center of mass. It does not go through the center of mass. So we will need to utilize the parallel axis theorem. Let me actually erase this equal sign so that it's sort of more obvious what I'm doing. So now we're calculating the moment of inertia contribution of this top rectangle here, shown by the IT, the I sub t. So we said we need to utilize the parallel axis theorem. What is I sub x? It is this equation here, where it assumes that we're taking it about the center of mass. So this is simply 1/12 times base, which is 6 inches, times h cubed, which is the height, that's 2 cubed, plus we have the area times d squared. So our area is 6 times 2, which is 12, and our d squared is 1 squared, which is also 1. So we have calculated this value. So this will be, let's see, that's 8. 8 times 6. That's going to be 4 plus 12 is 16 inches to the power of 4. So that's the value of our I sub t. And now let's calculate I sub b. So that will be, again, the same way where we do this equation to calculate that value. So that's going to be 1/12 times base, which is 1 inch, times height to the power of 3, which is 4 inches, plus we have the area here, which is 4 times 1, which is 1, times d squared. Now our d squared is 4 squared, so that's going to be 16. And when we calculate that, we get 69.3 inches to the power of 4. And when we simply substitute the values we have for I sub t and I sub b, we get the area moment of inertia equal to a value of 155 inches to the power of 4. And that concludes the problem.